Hello, everyone. My name is Rachel Baldwin, and I will be presenting my research on spatial analysis of groundwater quality across New Jersey watersheds, focusing specifically on dissolved oxygen and pH. These indicators help us understand overall watershed health and how human activity might be influencing groundwater conditions across the state. I'm going to briefly go over the introduction, background, methodology, results, discussion, and the conclusion. First up is the introduction. Water quality monitoring plays a huge role in environmental planning, especially in states like New Jersey, where land use changes quickly and watersheds are closely connected. Because water flows through hydrologic systems rather than political boundaries, using watersheds as the unit of analysis gives us a clearer picture of how pollutants move. In this study, I used dissolved oxygen, or otherwise DO, and pH as key indicators. DO reflects the balance between oxygen supply and demand in groundwater, and pH influences the chemical and biological processes that determine overall water quality. Since both ecological conditions and human activities vary across space, I also use spatial analysis tools in the program R to detect patterns and hotspots that traditional statistics might miss. Ultimately, the goal is to identify spatial patterns in DO and pH and test links to human influence. Background. Previous research has shown that watershed processes strongly affect how pollutants move through the environment. For example, studies have shown and others highlight how runoff and hydrogeology shape water quality. Urbanization is another major factor. Research has also shown how development, impervious surfaces, and wastewater inputs increase pollutant loading. DL and pH are commonly used indicators because they respond to environmental stressors like nutrient loading, low recharge, or industrial impacts. Spatial clustering is also expected in environmental data due to Tobler's first law of geography, which reminds us that near things are more related than distant things. Tools like Moran's eye and local indicators of spatial association help us formally test whether these patterns exist and where. For this project, I used several spatial datasets. First, the NJDEP Ambient Groundwater Quality Monitoring Network provided well level measurements for DO and pH from 2020 to 2022. I then used HUC12 watershed boundaries from FEMA and USGS to define the analysis units. To understand human influence, I incorporated population density from the NJGIS County dataset and urban land coverage from the 2015 New Jersey Land Use Land Cover dataset. Combining these datasets allowed me to look at both natural and human-driven influences on groundwater quality. New Jersey is an interesting study region because it contains a wide range of physiographic areas, from mountains to coastal plains. It also has a large population concentrated across the coast and metropolitan regions. Watersheds across the state differ not just in size, but also geology, land use, and development intensity. This creates a dynamic setting for assessing spatial variation in DO and pH. Methodology. I began by converting the groundwater wells into spatial point objects as they were originally character values and I kept getting errors. Then I aligned their coordinate system with the watershed polygons. Next, I used a spatial join to assign each well to the watershed it falls within. From there, I calculated mean DO and mean pH values for each HUC12 watershed. Then, I computed watershed level characteristics such as population density and percent urban cover to use as explanatory variables. To understand spatial patterns, I created a neighbor list for the HUC12 watersheds using Queen contiguity. I next then created spatial weights where watersheds were considered neighbors if they shared any boundary point. I then used this spatial structure to run global Moran's eye to test for overall clustering, and then ran local Moran's eye to find specific hotspots, cold spots, and outliers. These tools help reveal whether water quality values in one watershed are similar to those in neighboring ones. The results. When I modeled DO using population density and percent urban land coverage, the results were not statistically significant. The adjusted R squared was only 0.02, and neither predictor had a significant coefficient. The LISA results supported this. Although a few watersheds formed high-high or low-low clusters, most were classified as not significant, showing that dissolved oxygen does not exhibit strong spatial clustering. The global Moran's eye for DO was 0.15. But this was not statistically significant, and the residual Moran's eye showed the same pattern. Because no meaningful spatial dependence remained, I determined a spatial regression model was not required for DO. For pH, however, the results were very different from DO. The global Moran's eye for pH was 0.51, and this value was statistically significant, showing strong spatial clustering across New Jersey watersheds. The LISA map reinforced this pattern. Several high clusters appeared in the central and northern regions of the state, while low clusters were concentrated in the south and southwest. These clusters suggest that pH is shaped by broader regional factors such as geology or groundwater flow paths. When I modeled pH using population density and percent urban land coverage, the regression showed that urbanization was a significant positive predictor, but the residual Moran's eye remained high at 0.51. This meant strong spatial dependence was still present. Because of the moderately significant findings, I ran an OLS analysis which resulted in percent urban land cover being significantly associated with higher pH, while population density was not. However, the OLS residuals also had a Moran's eye of 0.51, meaning strong spatial autocorrelation remained. I continued to conduct an LM diagnostic test, which pointed specifically to spatial error process. After estimating a spatial error model, the AIC dropped by nearly 29 points, and residual spatial autocorrelation was eliminated. This indicates that a spatial error model is the appropriate framework for explaining the pH patterns. Discussion. I believe that these findings show that DO is influenced by more localized factors not captured by simple measurements of urbanization or population, while pH exhibits strong spatial clustering due to broader geological or hydrological factors. Urban land cover does play a meaningful role in predicting pH, but spatial error dependence must be modeled to avoid biased results. For management, this means municipalities should consider groups of neighboring watersheds rather than treating each watershed in isolation. Conclusion. In summary, water quality patterns in New Jersey are strongly spatial for pH and moderately spatial for DO. Urbanization raises pH slightly, but does not meaningfully affect DO in this dataset. Population density alone is not a strong predictor of groundwater quality. Spatial analysis proved essential, especially the spatial error model for pH. These findings highlight the value of spatially informed watershed planning and point toward future research that could include additional parameters, more years of data, and finer land use categories. Thank you so much.